we can go ahead and just introduce this session. So welcome everybody to the discussion of the nanocellulose session. There are two co-organizers of this session. So I'm Nicole Stark. I'm with the Forest Products Laboratory in Madison, Wisconsin. And Gloria, would you like to introduce yourself?
Sure. I'm Gloria Oporto, a faculty member in the School of Natural Resources and Resources at West Virginia University. I have been working here for 10 years now, and my main interests are focused on nanomaterials and its application in advanced composites and biomaterials from lignocellulosic specifically sources. So I'm very happy to be here and starting the discussion. Thank you.
Yes, and Gloria and I have put together a session for you this afternoon. We have 8 presenters in this session, so really excited to see that, and covers the gamut from production of cellulose nanomaterials to use in maybe more traditional forest products, and then use in emerging forest products applications. And so happy to hear from everybody today a little bit more about their presentation. What Gloria and I would like to do is just have each presenter introduce themselves and maybe a quick summary of their presentation. Hopefully everybody has had a chance to see most, if not all of these, to preview them. And so if each presenter has maybe like a 4-minute introduction, we can take a couple of questions for each presenter and then have some time at the end to have some questions for the overall panel. So what we would like to do is just go down the list here. And the first one is Yuqing Peng, whose presentation was characterization of cellulose nanocrystal suspension, rheological properties using a rotational viscometer. So Yuqing, would you like to introduce yourself in your presentation?
Okay, well, good to, I should say good afternoon, everyone, right? I'm Yuqing Peng, a assistant professor in the School of Forestry and Wildlife Science at Auburn University. Basically, I joined Auburn last January. Well, unfortunately, just 2 months later, everyone just went home. So, but I'm glad that, hopefully we can come back soon. Before I joined Auburn, I was in a Coca-Cola company working as a research engineering, mainly focused on the sustainable packaging research and development. And before that, I was a material scientist in a very global corporation, mainly focused on the packaging characterization, manufacturing, and design. At that time, my role is mainly focused on the plastic packaging. So I know a little bit about the thermoform injection molding, extrusion, all these different processes to make plastic packaging. Mainly the company very global is I think it's the largest polyolefin processing or converter. And before that, I was in the school from a Clemson University for about 2 years, and before that from University of Maine. And even further down there, I was Mississippi State for about 2 years. So basically, I covered my whole history in my academia, in the industry experience. So the presentation I put it on for this international convention is characterizing the cellulose nanocrystal suspension rheologic property, trying to use a simple, very convenient operation of a rotational viscometer. You probably see a lot of research from many different groups try to get the rheological property of this suspension using high-end rheometers. But sometimes, some lab may do not have a rheometer. So the motivation for this research, we're trying to see for a general, even in the pilot plant, laboratory, or production plant, how the the technical person can tell or differentiate the cellulose nanocrystal suspension, what's their rheological property. So the goal is trying to see what we can get from a simple rotational viscometer on the rheological property of this CNC suspension, because this rheological property is very important for many downstream handling suspension handling, drying, and application pumping, all is critical. So my study just focused on that part. We use a simple, just like a Brookfield, probably many of us were very familiar with the Brookfield viscometer. Similar viscometer, I just use that viscometer using different spindles and rotate the spindle in different speed, and then get to the torque. Based on that, to do the calculation to get the rheological behaviors of suspension. So we did characterize the suspension at different concentrations. We find that we can change, the rotation speed and get a very nice curve. It's basically it's a power law model fit to the shear sealing suspension. We can get a very nice curve, but the limitation of this technology is we have only a short range on the shear rate. And then if you go to see the literature, you find that probably the people propose a different method to calculate the real shear rate from this viscometer. So the study we did is just summarize what the different methods and then get the calculation on the viscosity. So which viscosity is getting, well, I should say it's more accurate. We summarized basically various 3 popular methods, and each method shows a different viscosity. So it depends on what method you use to calculate the real shear rate and also the final viscosity. You will probably get different results. And then some of the methods showing a big gap with each other. So basically, what we put in the presentation is what you need to pay attention to when you do the calculation, and what you can get from the viscosity of the suspension. And then we finally characterize the effect of different concentration of the CNC suspension on the viscosity. We figured there is a power law relationship. When the concentration of suspension increases from 3, 4, 5 to 6%, the viscosity is proportional to the third power of the concentration. So that's basically a whole study. It's a short, simple study, but we demonstrated that the rotational viscometer can be used to characterize the cellulose nanocrystal suspension in the lab or in the production plant. It's easy to do, and you can get a pretty accurate result. So we concluded that that's a method we can use to for the quality control or characterization of cellulose nanocrystal suspension. That's all the whole presentation. If you have any questions, I'll be happy to answer any questions or any discussions. Thank you.
Okay, thank you, Yu-Cheng. It's always great to find ways to measure, to characterize anything that is less expensive and faster for quality control. That's incredibly useful for the industry and moving it forward. If anybody has any questions, you can either raise your hand and ask them yourselves or put them into the chat, and then I'll read them out. Okay, so if we don't have any questions for Yu-Cheng now, at the end, when we have more of a panel discussion, we will have questions that any of the presenters can answer. Thank you.
Can I ask something, Nicole? Can I?
Yes, please.
Okay, good. So Yu-Cheng, very good presentation. Very nice also seeing you here. My comment is, so your main goal, right, was to prepare something simple that someone, right, in a lab, in a company can use, right, in order to characterize this type of materials. But in your conclusions, right, you are giving a very specific recipe. You are telling you should use this specific, the spin, right, for the specific material. In this case, cellulose nanocrystals, right?
Yeah.
So, and we know that, and you show and demonstrated that when you are changing the characteristic of the spins, the properties are changing. So I believe, right, that if you are changing your cellulose nanocrystal for cellulose nanofibers, you will see probably even more or different, of course, behavior. So can you somehow extrapolate, I mean, starting from what you discover, and using cellulose nanofibers? Can you assume that the recipe can be used as you are presenting, or what changes you will need to do in order to replicate your results?
Oh, that's a very good question. Actually, we did an extra experiment. The presentation here, we mainly focus on cellulose nanocrystals, and we tried the same method on the cellulose nanofibrils. But I just want to mention that that's two different cellulose fiber produced by different process, right? When we're trying to use the rotational viscometer on the nanofiber cellulose, actually it doesn't work. Okay. Since the longer fibers, probably the higher aspect ratio, it takes a long time to get a very consistent or stable readings from the rotational viscometer. And we takes a lot of time doing that, but obviously this probably is not a suitable method for the nanofiber cellulose. And for the extrapolation, we can use the model, the Power law model. We fitted the testing data with the model. We can extrapolate model to a specific shear rate range. But the limitation of this one is, as we know, if we go to we characterize the suspension in a full range of shear rate, at a very low shear rate and a very high shear rate. They are not a shear thinning or a Power law model anymore. That's the limitation of using this method. But if we have different, you say if you cellulose nanocrystal suspension from different manufacturers or from different plants, and when you're going to the production plant want use these different batches or different manufacturers, different suppliers, we can do a quick search, see at this specific shear rate range, will they behave the same? If they behave the same, we can make assumption they may function the same when we handling the suspension from different manufacturing plant or different batches. So that's the extrapolation we can do. But if we have some application in the very low shear rate range or very high shear rate range, just like when you do the paper coatings using some conventional coating process, the data we get may not be, you cannot put the exact data in what's the viscosity data you need in your calculation. You may still need to get that specific viscosity data in that specific shear rate range. So that's the limitation of this method. That's a very good question. Thank you.
All right, thank you. We'll move on to our next presenter, Jinwoo Wang. Jinwoo, if you can just introduce yourselves and give a summary as to your presentation, please.
Hello, everyone. This is Jinwoo Wang from Maine, University of Maine. I'm an employee of a colleague of Nico, but I'm located at the University of Maine. So my job is mainly collaborate with University of Maine's professors to do some cellulose jobs. So as you know, we all know cellulose has a very good barrier properties, oxygen barrier properties. So, so my research philosophy is to try to maintain cellulose and continuous bulk materials. That means I try to use the cellulose and a layer of materials and composites with other materials. So in my case, so I just mainly work with Professor Doug Gardner. We have project with Flamifa. We try to laminate cellulose with polymers like PP, PE, with different layers. So the point is the cellulose has a good oxygen barrier, but not the water vapor barrier. So polymers have a good water vapor barrier, but not oxygen barrier. So if we laminate this together, so we can possibly create some both good water vapor barrier and also good good oxygen barrier material. So this is one area. The second area is we try to use the paper based materials for package. So and you know, we all know paper is a porous material. So we collaborated with Professor Bothfield. So try to apply a layer of the cellulose nanofibril on the paper-based paper. And then also, you know, we still need to get a code of the polymer to for the water barrier. So my prediction mainly summarize these two. One is laminated or polymers and cellulose nanofibril, cellulose non-cellulose film, and another is paper-based coating. So that is all my two jobs. Thank you.
Okay, thank you. Do we have any questions for Jinwoo?
Hey, Jinwoo, I have a quick question.
Mm-hmm.
So when you coat the nanocellulose on the paper-based substrate, what's your goal? Are you trying to improve what kind of properties of the paper substrate?
So they have two purposes. One is improve the oxygen barrier. Two is improve the grease resistance. So so typically paper doesn't have oxygen barrier. Paper also is doesn't have the grease and oil resistance. So we increase this cellulose to try to improve these two properties.
Okay. Following question is, are you using the nanofibril cellulose or just cellulose nanocrystals?
We use cellulose nanofibrils from the University of Maine.
Okay. Thank you.
Okay, thank you. We'll move on to our third speaker, who is Alex Berg. Alex, would you please introduce yourself and give us a quick summary of your presentation?
Thank you very much, Nicole. Hello to everyone. I'm speaking from Chile. I work in an institute. It's called Unidad de Desarrollo Tecnológico in the University of Concepción. We're approximately 100 people who work closely together with companies developing technology for making a better use of sub-products of the forest industry. To my paper, co-authors are José Fuentes, Juan Sea, and Gustavo Cabrera Barjas. About the topic we worked in our paper. Let me see, as an introduction, we compared the reinforcing action of acetylated as well as non-acetylated nanocellulose. And we use it in plastic and in wood adhesives. What we observed, a better dispersion on the one side, but also a lower tendency to re-agglomerate between the dispersed nanofibers, and certainly also better mechanical properties of the reinforced material. Based on this, and also having in mind that we want to upscale the technology, we studied the fibrillation of eucalyptus kraft pulp in a pilot plant scale by means of a 12-inch refiner and a homogenizer, as well in water as in acetic acid, in concentrated acetic acid. What we observed, our results are practically four. On the one side, the fibrillation of nanocellulose is possible as well in water as in an organic solvent, in our case, acetic acid. But a little more energy is needed if an organic solvent is used. Second result, the acetylation is possible, and this is important, is possible without acetic anhydride and without a catalyst. Only with concentrated acetic acid at a temperature of 120 degrees or more, a partial acetylation is possible to achieve. Our third result is the degree of substitution of the cellulose under the same acetylation condition depends on the fibrillation degree of our nanocellulose. If a higher specific surface is available, the degree of substitution rises. And the fourth result, and in our opinion, the most important, the reinforcing action of nanofibrils in commercial urea formaldehyde resins is clearly superior if we fibrillate the fibers in acetic acid in comparison to the water media. So that is our paper. We think it's a very interesting, or the results are very interesting, and we're working nowadays in upscaling the technology related to these results.
Okay, thank you. Do we have any questions for Dr. Berg?
I'll ask a question. So I see in your work, actually good presentation. I think it's very interesting. I see that in the work that you did, you use basically a lot of mechanical energy to produce these fibers. My understanding is that some people have used acetylation to help reduce the amount of energy to disintegrate fibers. Can you talk about maybe how can we get these fibers acetylated without having to add so much energy?
Yes, you see it's a different result. If you first acetylate the fibers and after do that, you do the refining, it's true, you can decrease the energy you use. Yeah, but what we did the acetylation after that, not before. Yeah, so in that case, certainly the energy is not reduced. Now it's true. We put a lot of energy. We also wanted to see all the range between 15 cycles to 45 cycles. Now this can be reduced principally in the homogenization step because it depends on the gap of pressure. We utilized, because we used acetic acid, we could not use another equipment, only 200 bars of a pressure drop. If you use, for example, 1000 bars, certainly the step can be reduced drastically. We know it because we have done it in water media and we can see it.
Okay, other questions? All right, let's move on then. Our next speaker is Dilpreet Bajwa. Dilpreet, if you could please introduce yourself and summarize your presentation for us.
All right. Good morning, good afternoon, or good night, wherever you are located. So again, the title of my presentation is Improvements in Dispersion, Thermal, Mechanical Properties of Polymer Composite Using Silane Functionalized Cellulose Nanocrystals. The collaborators on this project, which is funded by NIST, is again Nicole Stark from US Forest Product Lab. And then I have a collaborator from North Dakota State University and Greg Holt from USDA ARS Cotton Processing and Production Center. So probably all of you are very familiar with one of the problems we have with the cellulose nanocrystals is dispersion in polymer matrices. And there is a lot of work going on in this area, how we can disperse cellulose crystals in polymers. So my group actually has been working with the cellulose crystals for last 7-8 years. And we are working on this challenge. And we found that, and that's kind of reported already in literature, that if you add some functional groups on the surface of cellulose crystals, that they help in improvement in dispersion in the polymer matrices. And there are several methods already reported, both chemical and physical, including polymer grafting, silation, acetylation, acid functionalization, and among physical ultrasonication, plasma, and electrical pulses. All those are well known, and there's a lot of information available in public domain about these methods. So our group, or in my research, we wanted to see how, if we can treat CNC with silane, whether they will help, that will help us to disperse these crystals in the polymer matrices. And we tried to treat the CNC with, again, silane, and we used polyethylene matrix. We wanted to initially see what is the optimal silane treatment that would help to improve dispersion. So we used polyethylene oxide 1 million grams per mole molecular weight, and then silane 3-amino propyl ethoxysilane. That was the silane treatment we gave. And there were different levels of silane treatment. We looked at 1-to-1 ratio, 1:2.5 and 1:5%. So we treated, again, PEO is water soluble, CNC and silane. So we did not have a problem with blending these solutions. So we created these films with a different silane functionality, amount of different silane on these, and we try to characterize both the CNC modification, whether the amine was attached to the cellulose as nanocrystals, and also we looked at under the TEM whether there was improvement in dispersion, because that was one of the main goal of this research. And obviously we looked at how the properties, whether mechanical properties improved using DMA, DSC, crystallinity, we looked at it, and as well as we did the thermal analysis to see if there is any improvement in the thermal stability of these composites we got out of PEO and functionalized CNCs. So what we found through FTIR, that we were able to see in the samples that the amine groups were, the silane groups were attached to the CNC, and through the FTIR, the characteristic stretching and bending vibrations were observed for the amine band. The second thing, what we observed was that when we looked under the TEM, that the composites films with 1% PEO and 1% CNC and 1% silane showed the best dispersion compared to the formulations where the silane was either 2.5% or 5%. The next thing, we also noticed that there was an increase in the thermal stability with the increase in silane amount in the system. The increase in the thermal stability was attributed to polysiloxane network grafted onto the surface of the CNCs. And similarly, the highest crystallization or the crystallinity was observed in the samples with 1% silent treatment. And that crystallinity was around 55.14%. And again, among all different formulations, the formulation with 1% silane, 1% PEO, and 1% CNC had the highest storage modulus compared to others. And we try to keep the cellulose nanocrystal amount same in all the formulations. And if you will look at the presentation, so PEO was kept at 1%, and CNCs were also kept at 1%. So only the variable we changed was the silane treatment. And then overall, from this study, which is still continuing, we found that the 1% silane treatment for 1% CNC was the most effective. It helped to improve the thermal properties, mechanical properties, as well as helped the dispersion of CNCs compared to 5% or 2.5% treatment. We also found that increase in the silane concentration above 1% led to decrease in storage modulus, increase in 10 delta, and thermal degradations. So going forward, we are now looking at using these silane treated cellulose nanocrystals in the high density polyethylene matrix and see how if we are able to replicate the results that we saw in the PEO polymer. Although PEO was hydrophilic polymer, now HDP is going to be hydrophobic. So we are going to see in the next couple of months that how this functionalization helps us in hydrophobic polymer matrices. So that is the nutshell what our research findings were, that overall the 1 to 1% CNC and silane helped us to improve the properties and dispersion in the PEO matrix. And I'll be open to any questions.
Okay, thank you, Dilpreet. Do we have any questions for him?
I have a question. Dilpreet, can you talk a little bit about the method of how you did the silane modification, specifically the drying part, or how you did the water removal? Did you do the water removal in the presence of PEO?
So what we did in this was, first what we did was we dissolved the PEO in distilled water, DI water, and then we added CNC. That was the second step. And then again, this was against constant stirring. And then we added silane, different levels of silane. And these were all done in a beaker. And once the solution was all clear, and we poured the solution into Petri dishes that were Teflon coated, PTFE Petri dishes. And then we let these dry for 24 to 48 hours. And then we picked the film that was dried film out of these Petri dishes, and then we evaluated the properties, both look for dispersion of cellulose crystals as well as mechanical properties. And like I said earlier in my presentation, the two formulations where silane amount ratio was 2.5 and 5 times the CNC, there were big clumps. We didn't see very good dispersion. Only 1 to 1 was the best dispersion we noted. Did I answer your question?
Okay, thank you. And if you come up with questions or have questions as we move along here, enter them into the chat and I'll read them at the end. Hoping there's a little bit of time at the end just for questions for the overall panel of presenters also. Our next presenter is Mehdi Tajvidi. Mehdi, will you please introduce yourself and summarize your presentation?
Hello, do you hear me, Nicole?
Yes, and welcome.
Okay, sorry, I was late. I'm just off the other presentation. So yeah, my name is Mehdi Tajbidi, and thank you very much for having me here. I'm the Associate Professor of Renewable Nanomaterials with the School of Forest Resources, the University of Maine. So Nicole, Jennifer told me quickly what I didn't understand. What am I supposed to do? Going quickly over my presentation?
Yeah, in just a few minutes, if you could summarize it, that would be great.
Okay, so with no slides or anything. Okay, so yeah, so I presented in the recording, of course, is our latest efforts of doing work on cellulose nanofibrils. So from all different types of cellulose nanoparticles that are out there. My research is mainly on cellulose nanofibrils that we produce here at the University of Maine. And the main focus is to use it as binder for composite applications. So the story goes back to about 2014 when we first started using nanocellulose as binder for particle board production. And the idea was to replace urea formaldehyde resin with fully with nanocellulose. Within that research, of course, the biggest issue was how to remove water from nanocellulose and from the system when you mix these together. And we figured out basically a natural phenomenon that now we call contact dewatering as a way to remove a lot of water without any heat application. Basically, we see that when nanoparticles of nanocellulose are in contact with a surface with high surface area, high specific surface area, like small wood particles, then the bound water in the nanocellulose basically turns into free water, and water is now free to be easily removed. And that system basically helps you do a lot of different designs with the product. And we went from anywhere from particle board, went into fiber board, and then most recently into wall board, gypsum board panel type replacement, panels that do not have any gypsum in them, just wood particles and nanocellulose. And then we are also getting into molded shapes and interior wall coverings and panels. And the very recent things that we are working on are on using nanocellulose binder along with wood fiber, different types, to make like a styrofoam packaging material replacement. That's basically in general what we are doing around the binder application of nanocellulose, and I personally think there's a lot of potential around this technology.
Okay, thank you, Mehdi. Yes, there are a lot of applications there. Do we have questions for Mehdi?
I have another question.
Yeah, go ahead.
You're on.
So can you talk about a little bit about the dewatering or press times and maybe how these compare to sort of traditional fiberboard processing, and maybe what you can do to improve that dewatering process?
Yeah, so the dewatering that we first started with was actually one-time dewatering. And in one-time dewatering, we get to about 50% solids of our system. So on dry basis, it's about 100% moisture content, as we wood scientists like to call it, right? And if you press such a thing in a press, the press time, the hot press time, is actually pretty long at this time. It's about 45 minutes, so which is much longer than what it should be for regular particle board. So that's why the main reason that we shifted from particle board now into wet formed fiberboard and dry wall systems, where you don't really actually do hot pressing. Instead, you actually dry the material in a large oven. So that's the new direction that we are taking now.
So, Mehdi, I have a question that's a kind of two-part. One is, what percentage of nanofibrils you add to these wet boards, and how do you make they are dispersed?
Well, I can talk about dispersion first. Dispersion is actually very easy. You have a lot of water in the system, and as far as you have water so that the wood particles get wet, you get very good dispersion. I don't see any issues around that. The second part was, what was that? I forgot.
What percentage of?
Oh, the percentage. The
Yeah.
percentage, we have worked anywhere from about 10% up to about 20, 25%. At 15%, you can get what you want. Depends on the density of the panel that you want to make. But generally speaking, the higher density you go, the lower amount of nanoparticles you need. The lower density you go, the more nanofibers you need.
Thank you.
Sure.
Okay, thank you. And then we'll move on. So our next presenter is Matthew Dunlop.
Thank you, Nicole. Hello, everybody. It's a pleasure to be with you today. And I've enjoyed very much hearing everybody's talks. And now I'm going to tell you a bit about mine. So as you can tell, it's generally titled The Scalable Isolation of Cellulose Nanocrystals from Invasive Tunicates. Now, I'm from Canada, and actually I'm specifically from Canada's smallest province. It's a little island on our east coast known as Prince Edward Island. And on Prince Edward Island, aquaculture is a very big thing, particularly mussel fishery. Now, tunicates are an invasive species, a marine animal that has been really troubling our mussel fishing community, as well as our local aquaculture community in general. And how we've dealt with it on PEI is to mitigate and contain the problem. But unfortunately, the problem is continuing to grow, and thus a different direction is needed. And so my PhD thesis research has been to develop a new process for dealing with these invasive tunicates. Rather than contain and mitigate, we seek to harvest and utilize them for our local benefit. And so my thesis has basically been taking these tunicates, increasing the scale of nanocellulose, specifically CNC production from these tunicates, and trying to find different ways to utilize the CNC to justify our increased scale. I work between the Department of Chemistry and the School Faculty of Sustainable Design Engineering, and my supervisors are Dr. Bishnu Acharia, who's now at the University of Saskatchewan, and Dr. Rabin Bersisser, who is here at the University of Prince Edward Island. The research started by using small pressure vessels to take gram scale quantities of tunicates and convert them into sub-gram quantities of CNCs. And then we built off of that to start looking at larger and larger process inputs. In fact, I had the good fortune a number of years ago of getting to work with some colleagues from the Forest Product Laboratory, including Dr. Ron Sabo, who's on the call with us, where we took tunicates from Canada, from Prince Edward Island, brought them to the Forest Product Laboratory, and processed them into CNCs. When we reported that in literature, it was the largest production scale of tunicate-derived CNCs that has ever been reported. And we've actually brought some process improvements back with us to Canada now, where we're working on an even larger scale. And so at this point, we're looking at 200 kilograms of raw material going into our process. And we're hoping to continue to build that into what one day might be a commercial process. I also spent a little bit of time in the presentation talking about some of the ways we've used the CNCs. Tunicate CNCs are unique and distinct from wood CNCs in that they have a higher aspect ratio. They're much longer. And as a result, they can complement wood CNCs in a variety of different applications. And in fact, we've actually gone what I think is a further step where we've looked at combining wood CNCs and tunicate CNCs. The idea being that a combination of high aspect ratio and low aspect ratio fillers together within a common polymer matrix may provide unique reinforcement unique properties to the materials that they're reinforced with. The first study, we looked at polyvinyl alcohol and combined high aspect ratio tunicate CNCs and low aspect ratio wood CNCs within that polymer matrix. And we found synergistic mechanical reinforcement, specifically looking at the elastic modulus. Now it's an early study and it looked at specifically cast films. So we wanted to kind of build off that and see if we could do something a little bit more relevant to industrial practices. And actually working with Dr. Sabo at the Forest Product Laboratory, we used polylactic acid as another matrix to try and see if we could do extrusion melt mixing processes with these CNCs and preserve this hybrid reinforcement. So using PLA, we prepared cast films and extruded films by solution mixing and melt mixing techniques. We noticed that in the solution mixed films, this hybrid effect we observed in solution mixed polyvinyl alcohol composites was preserved. However, the hybrid reinforcement was not observed in the extruded composites, but we think that that the reason why this is perhaps happening is because there was also severe aggregation seen in these composites, as is expected with PLA CNC materials. In any case, we're working on other polymers systems of interest to try and elucidate whether this hybrid effect might have other applications outside of just research. We haven't found the right one yet, but we're still working on it, and we hope to develop something in the near future that will allow us to show just how useful tunicate CNCs can be to those who currently use lower aspect ratio wood CNCs. In fact, perhaps even opening up new applications. So that's basically what my talk was about, and a little bit about where we're coming from here. I look forward to your questions if you have any, and to hearing about everybody else's talks. Thank you.
Okay, thank you. Do we have time for a quick question?
Can you do you know what is the yield of your CNC from the waste based on the raw material?
The yield of CNC based on the raw material, based on the raw tunicates. Gotcha. Based on the dry weight, we're talking low percent. How should I put this? We measured a number of different ways. If you're looking at 200 kilograms of wet raw tunicate input, you would expect to get 1 kilogram of dried tunicate CNC. Now, the CNCs are generally never dried, and we actually we prepare them as a 1% suspension after filtering out the salts and such from hydrolysis. And so as a result, you end up actually getting about 100 kilograms of 1% CNC suspension from 200 kilograms of raw tunicate input. So two different ways to think about it, but that's our yields, more or less.
Thank you.
Welcome.
Okay, thank you. Moving on, our next presenter is Kunyang Lee. Can you please introduce yourself in your presentation?
Thank you, Nicole. Hi, my name is Kunyang. Hopefully everything is working here. I'm an academic at Imperial College London, so it's almost 7 o'clock at night for me. The presentation that I have for this conference is on upcycling waste with nanocellulose. Effectively, you get a bunch of loose fibers, whether it's chicken feather fiber or natural fibers or whatever that it is. Typically, you need a polymer to bind them together. In our case, we actually use nanocellulose with its effect to form irreversible hydrogen bonds together, and we use that effect to actually bind these loose fibers together. We are able to demonstrate in this particular presentation that the bending properties of these nanocellulose enhanced fiber board, if you will, it's stiff, it's rigid, and under the right condition, in the case of a chicken feather, you are able to deconstruct the whole thing, recover the chicken feathers again. So effectively offering you a sort of structural component where you use nanocellulose to bind a waste fiber together, use it for a certain period of time, deconstruct them, and then digest them, if you will. I'll keep it very short and brief here in the interest of time. So if there's any questions, please feel free to drop me in this chat, or just the presentation is there for you to look at. Thank you.
Okay, thank you. Do we have, do we have any questions for Kunyang? It looks like we lost our presentation slide. But our next speaker, just moving forward in the interest of time, is Ron Sabo. Can you please introduce yourself and give us a summary?
Hello, I'm Ron Sabo. I'm a research materials engineer at the Forest Products Laboratory in Madison, Wisconsin. The project that I gave a presentation on is wet compounding of cellulose nanocrystals in PLA. This is a collaborative project between the Forest Products Laboratory and Michigan State University. So really the motivation is to create sustainable materials for packaging. And in the case of this work, we're really looking at trying to improve biopolymer films. So looking at PLA in this case, the problem with these biopolymer films is that they are poor barriers, so that they are not very good for packaging applications. And so we want to add cellulose nanomaterials to improve the barrier properties of those polymer films. And so there's really a few objectives that we had for the work. And one is to figure out ways to compound these especially how to deal with all the water that you have with nanocellulose. And so we're working on this wet compounding process to help us blend the composites. And I'll talk a little bit more about that in a moment. A couple of the other things that we are looking to sort of do with this work is to develop new formulations to help improve dispersion and adhesion, and then also to demonstrate that these materials work as packaging materials. So for wet compounding, what we're really talking about is trying to combine suspensions of nanomaterials, especially nanocellulose, directly with polymers without having to first dry nanocellulose. And this can be done either in continuous or batch processes. And then when you feed the materials in, you typically get some steam coming out, and often you'll have water dripping out of these machines. And then also a composite that can come out. So essentially we're talking about blending suspensions of fillers with polymers without having to dry them first. And so we're not the first ones to do this type of work with cellulose nanomaterials. So Craig Clemens and I wrote a review paper. So I encourage you to check that out if you're interested in this wet compounding and polymers this year. So specifically in this work, though, we use a thermokinetic mixer, which is a batch process. And the way this thermokinetic mixer works is that it's works on viscous heating. So basically it has impellers that have a close tolerance to the chamber, and you feed the material in, and as the impeller turns at thousands of RPMs, it has enough friction to heat up the material, drive moisture out, and melt the polymer. And so we can discharge that molten polymer and then process it in cells. And so we found that we got much better dispersion using wet compounding, especially if we use good formulations or appropriate formulations. And we were able to even produce some composites with about 10% CNCs with virtually no loss in measured transparency. And so we're hoping that we could eventually create a process where we're doing sort of a master batch compounding with using this wet compounding process, and then those compounds could be directly fed into existing manufacturing processes. FPL, we just got a new kinetic mixer, and since COVID is dying down, I'm excited to get back in the lab and hopefully advance this work a little further. And so I'll just leave it at that, and happy to answer any questions that you might have.
Okay, thank you, Ron. Do we have questions for Ron?
Ron, this is Dilpreet from Montana State. I have a question now. So when you do this kinetic mixing, do you see any change in the properties of PLA? Does it get—
Not really, no. Hardly any changes at all. So we also have done various studies with nylon and other types of polymers, and in some polymers you'll actually see a crystal structure change happening just because of the presence of water. Now, if we have seen some molecular weight degradation if we have very long residence times, especially. So one advantage of this kinetic mixer is that it can process in the absence of water in like tens of seconds. You can do compounding. In the presence of water, it's a little bit longer, but if we don't put too much water and we use high speeds, we can do this in less than a minute. And so we found on the ones that were less than a minute cycle time that we didn't have any degradation in molecular.
What was your batch size?
Sorry, say that again.
What was your batch size?
Oh, the batch size. So that varies quite a bit. I think in the study that I presented here, we're in around the 200 gram range. Craig Clemens found that batch size does affect dispersion. So we were kind of disappointed to see that you get better dispersion, you use a smaller batch.
Thank you.
Okay, any other questions? So we do have 3 or 4 minutes left here for questions. If anybody has thought of questions for our entire panel of presenters. First, I want to get to one. Kunyang had one for Jinwoo. So Jinwoo, this is for you. How thin can we go with the layered cellulose composite packaging before we start losing barrier properties? How thin can you go?
Okay, Nico, would you repeat again? I'm sorry.
How thin can you go with your layered cellulose composite packaging before losing barrier properties? How thin can you make your layered composites?
I'm trying to understand what the question is.
It's probably easier if I just jump in here. So effectively, normal plastic packaging, they are about 100 microns, 150 microns or so, and it works. but with cellulose paper and nanocellulose coating and with all the different multi-layer packaging, how thin can we go such that we are still able to compete with these sort of polypropylene PET type packaging? Because paper itself is quite thick on its own to even achieve the barrier performance that you mentioned in the presentation.
Yes, that is a very good question. My opinion, we never can achieve that thin paper-based materials as compared with the PP or PE other polymers. So basically, is we ask people to have some green consciousness. That means you choose this one not because this paper-based material is better than the polymer. So for example, for paper-based, if we need to code the C and F on paper-based materials, at least we need to code it around like 10 to 12 grams per square meters to achieve oil resistance. So for other kinds of laminated with polymers, also we need substantial thickness of the cellulose layers to achieve good oxygen barrier. So exact numbers, I try to recall what exactly. So we usually probably like at least like cellulose layers at least like 20 microns or 30 microns to achieve some reasonable oxygen barrier.
Thank you.
All right, thank you. And I would like to thank all the presenters today. I think this entire session has shown really the breadth of nanocellulose work that is being done. So thank all of you for your participation. Gloria, do you have anything you'd like to add?
No, I have been learning a lot. I have to confess that watching your presentations, I have many questions here, but time is not enough. Thank you very much. And a special thanks to Alex Berg, my former boss. So thank you so much for being here. And we really like to see more presentations from Chile, Alex. So I will be asking you for more for next year. So thank you, everybody. Really like to be here today.
Thank you.
Thank you.
Thank you, everyone.